What's up everyone, it's Stack Lessons here. Welcome back to the channel. Today we're diving into Amazon Web Services Glue Core, Catalog, Crawlers, and ETL. Let's get into it. By the end of this video, you'll understand the three building blocks of Amazon Web Services Glue, the catalog, crawlers, and ETL jobs, well enough to answer the single most heavily tested topic on the Data Engineer Associate exam. Glue is referenced in more task statements than any other service, so if you only deeply learn one thing from this course, make it this. Let's get into it. Open the official exam guide and count how many times Amazon Web Services Glue appears across the 4 domains. It shows up in ingestion, in transformation, in storage management, in operations, basically everywhere. So when candidates ask which single service is worth the most study time, the answer is obvious. Master Glue, and you've conquered the single biggest chunk of the exam. Before we go further, a quick heads up. Amazon Web Services has over 200 services, and this episode alone is going to name drop several of them. Don't panic. Every service that actually matters for this exam gets its own dedicated episode later in the course. And the first time a new name comes up, I'll give you a 1-sentence description so you can follow along. You don't need to know any of them in detail right now. Before we talk about what Glue is, let's talk about the problem it was built to solve. The first problem, your data is scattered across S3 buckets, relational databases, NoSQL tables, streams, and SaaS apps. The second problem, it comes in every format imaginable: CSV, JSON, Parquet, Avro, ORC, log files, and weird proprietary blobs. The third problem, nothing centrally knows what data exists, where it lives, or what its schema looks like. And the fourth problem, before you can query or transform anything, you need to discover it, organize it, and reshape it. That 4-part challenge is exactly what Glue was built to solve, and the rest of this video is about how it solves each piece. Glue answers that 3-step problem with 3 building blocks. First, crawlers are the discovery layer. They walk through your data and figure out what's in it. Next, the data catalog is the organization layer, a central metadata store that records what each dataset looks like. And finally, ETL jobs are the transformation layer, serverless Spark jobs that read, reshape, and write the data at any scale. The whole thing is fully managed and serverless, so you pay only for what you actually run. Here's the mental model I want you to hold onto for the rest of this episode. Imagine an unorganized warehouse. The crawlers are the inventory clerks who walk every aisle and write down what's on every shelf. The data catalog is the master spreadsheet they produce, listing exactly what's where. And the ETL jobs are the movers who actually pick things up, repackage them, and load them onto the right trucks. 3 roles, 1 coordinated operation. Let's ground this in our recurring company from episode 1, NexaRetail. Their data is stored in 3 main places. First, Amazon S3. Think of S3 as a massive cloud hard drive for any kind of file. That's where their clickstream JSON logs and partner CSV drops land. Second, Amazon RDS, Amazon Web Services Managed Relational Database Service. They run the database server, you just use it. That holds orders, customers, and inventory. And third, DynamoDB, a fast key value and document database where you look things up by ID. That's powering their shopping carts and session state. 3 totally different systems, 3 totally different formats. And Glue is the service that brings them all together. Let's start with the catalog because everything else in Glue revolves around it. The Glue data catalog is a persistent, region-scoped metadata store, and there is exactly one of these per Amazon Web Services account per region. Inside the catalog, metadata is organized into databases and tables, just like a relational database schema. Each table records the column names, the data types, the partition structure, and the physical location of the data, whether that's an S3 path or a JDBC connection. And critically, the catalog stores metadata only. Your actual data never moves. It stays right where it was in S3, in RDS, in DynamoDB. That separation is the single most important property of the catalog, and the exam tests it constantly. Here's how Amazon Web Services puts it in their official developer guide. The Glue Data Catalog is your persistent technical metadata store in the Amazon Web Services cloud, and each Amazon Web Services account has one Glue Data Catalog per Amazon Web Services region. That second sentence is the part that shows up on the exam. One catalog per account, per region. Memorize that. If the warehouse analogy isn't sticking, try this one. The Glue Data Catalog is the library card catalog, not the books. It tells you exactly which shelf each book is on and what's inside the book: title, author, page count, subject. But the books themselves still stay on the shelves. So if you delete an entry from the card catalog, the book is still there. The same is true in Glue. Deleting a catalog table never deletes a single byte of S3 data. Now here's a single sentence that explains why the catalog is so powerful. Amazon Web Services says it's a drop-in replacement for the Apache Hive metastore. The Hive metastore is the metadata standard that the big data ecosystem has used for over a decade. Spark, Presto, Trino, Hive, all of them speak it. So because Glue's catalog speaks the same protocol, any tool that already knows how to talk to a Hive metastore can talk to the Glue catalog without modification. That compatibility is the foundation of the next slide. Because the catalog is Hive-compatible, multiple query engines can share it. Athena queries it using serverless SQL directly over S3. Amazon EMR, Amazon Web Services managed Hadoop and Spark platform, pulls schema definitions straight from the catalog through the Hive metastore interface. Redshift Spectrum bridges your data warehouse and your data lake, letting Redshift reach out and query S3 files using those same catalog tables. And the pattern here is huge for the exam. Define a table once in the catalog, and every engine in the Amazon Web Services analytics ecosystem can query it without you redefining a single column. So that's the catalog, but how does it get populated? You could write the table definitions by hand, but for most data lakes you let Glue crawlers do it for you. A crawler connects to a data store, S3, RDS, DynamoDB, or any JDBC source. It walks through the data, samples it, and figures out the schema automatically. It then writes those table definitions into the data catalog, no DDL required. And on subsequent runs, it detects new partitions and new columns, keeping the catalog current as your data evolves. That last point is what makes crawlers a fit-and-forget piece of your pipeline rather than a one-time setup task. Now the crawler doesn't magically know what format your data is in. It uses something called a classifier. A classifier is a format detector, plain and simple. It reads a sample of the data and decides this is JSON or this is CSV with these particular columns. It returns two things, a proposed schema and a certainty score from 0.0 to 1.0. That certainty score is what determines whether the crawler trusts the answer. Hold on to that because it's about to matter a lot. Think of classifier priority like a hiring panel deciding who reads your data. Your custom classifiers are the hand-picked specialists, and they interview first. If one of them is completely confident, a certainty score of 1.0, you hire them on the spot and the schema is locked in. The gotcha here is that if you put a custom grok pattern at the top and your data is actually JSON, your specialist blocks the built-in JSON expert from ever getting a turn, and you end up with a broken table. On the right, if no custom classifier scores a perfect 1.0, Glue brings in the standard candidates, its built-ins in the fixed order shown on screen. Now here's the nuance most people miss. Glue doesn't immediately give up after the first round. It picks whoever scored highest across everyone who interviewed and uses that result. So a custom classifier returning 0.8 still wins if nothing else scores higher. The table only gets marked unknown when literally every classifier returns 0.0, when no one on the panel has a clue. And here's that rule in Amazon Web Services' own words. Glue invokes custom classifiers first, in the order that you specify in your crawler definition. And if a classifier returns certainty equals 1.0, that means it is 100% certain it can create the correct schema. Those two sentences are exam gold. I have seen this almost word for word in practice questions. Now, crawlers can run in two different modes, and the difference is huge at scale. On the left, crawl everything is the default. Each run lists every single object in the S3 target to figure out what changed. That works fine on a small bucket, but on a bucket with millions of objects, it becomes slow and expensive. You're basically recounting the whole warehouse every night. On the right, crawl event mode flips the model around. Instead of listing everything, S3 fires events whenever objects are added or deleted. Those events go into a standard SQ, and the crawler reads the queue to figure out which specific folders actually changed. One thing to know for the exam, it has to be a standard queue. FIFO queues are not supported because S3 event notifications can't be sent to FIFO. The first run is still a full scan, but every run after that is incremental. And there's one hard cap to remember, a maximum of 100,000 SQS messages per crawl run. That number shows up on the exam. Picture NexaRetail's clickstream bucket and look at three numbers. First, crawl everything runtime. Their nightly crawler ballooned to over 4 hours and started timing out completely. Second, crawl event mode runtime. After switching with S3 events feeding into SQS, the same crawler finished in under 5 minutes. Third, objects newly added per day, around 10 million new objects landing in that bucket. That's the scale driving these numbers. Same data, same catalog updates, just a smarter way of figuring out what changed. That's the kind of cost and performance win the exam loves to test. Okay, let's take stock. The catalog tells us what data exists and crawlers keep it current. But none of that actually moves or reshapes the data. That's the job of Glue ETL. You author your job in PySpark or Scala if you prefer, using Glue's extended API on top of standard Spark. Glue provisions the workers, runs the job, and tears them down when it's done. Those workers come in different sizes to match your job's memory and CPU needs, and we'll go deeper on sizing in a later episode. And billing is per DPU hour of actual runtime, where DPU stands for Data Processing Unit, so there's no idle cluster sitting around and no always-on cost. That serverless model is what makes Glue ETL fundamentally different from running your own Spark cluster. Now here's the most important conceptual distinction in Glue, and it shows up constantly on the exam. On the left, a standard Spark data frame is strict. It requires a fixed schema up front, and if it sees mixed types in a single column, it usually gives up and just calls the whole column a string. Data frames are fast and efficient on clean tabular data, but they break badly when schemas drift. On the right, Glue's dynamic frame is flexible. Each record is self-describing, so no schema is required initially. Glue computes the schema on the fly as it reads, and when it finds a column with mixed types, it doesn't panic. It encodes the conflict as a choice type, which is essentially a union of all the types it saw. That makes dynamic frames purpose-built for the messy, semi-structured real-world data you actually encounter. Here's the cleanest way to think about a dynamic frame. According to the official Glue documentation, a dynamic frame is similar to a data frame, except that each record is self-describing, so no schema is required up front. Glue computes a schema on the fly when it needs one, and when records disagree on a column's type, it explicitly encodes that mismatch as a choice or union type. The phrase to anchor on is self-describing records. That's the entire reason dynamic frames exist. If a dynamic frame contains choice types, you have to resolve them before you write to a fixed schema sink like Redshift or Parquet. That's what ResolveChoice is for, and there are 5 strategies. First, cast forces every value into one specific type, and anything that can't be cast is silently turned into null, a sneaky way to lose data. Second, make calls splits the choice column into 2 separate typed columns. Third, make struct preserves every variant together inside a single struct column. Fourth, project keeps only one type and drops records that don't match. Fifth, match catalog forces the schema to align with an existing catalog table definition. The exam tests all 5, so know exactly when each one is the right tool. Cast when you trust the data, make calls or make struct when you need to keep both variants, project when you want to filter, and match catalog when downstream schema is the source of truth. Don't get lost in the syntax here, the shape of this code is what matters. Amazon Web Services has a public Medicare dataset where one column contains a mix of longs and strings, which is a perfect real-world example of the type conflict we just talked about. The pattern is 3 steps. Load the data as a dynamic frame from the catalog. Call ResolveChoice with a spec that tells Glue what to do with the conflicted column here, cast it to long so string values become null. Then convert to a Spark data frame once the types are clean. That's the takeaway worth remembering. Always ResolveChoice before you convert to a data frame or write to a strict format like Parquet. Now let's talk about a real-world pain point you will absolutely hit in production, and that the exam tests directly. Spark spawns 1 task per input file. So if your S3 prefix has 200,000 tiny JSON files, Spark spins up 200,000 tasks. The overhead crushes the job, the driver runs out of memory, throughput collapses, and your job runs for hours making almost no progress. Real engineers complain about this constantly on forums. Glue has a one-line fix for it. The fix is the groupFiles connection option. When you create the dynamic frame, you pass groupFiles set2 in partition, which tells Glue to bundle many small S3 objects together into a single in-memory partition during the read. You can also set group size in bytes to control the target chunk size. 1 million bytes is a common starting point. That single option can turn a multi-hour job into a 5-minute job. One caveat to memorize for the exam: groupFiles works for CSV, JSON, XML, IN, and GrokLog. It does not work for Parquet, Orc, or Avro, because those columnar formats already do their own native grouping. And here's a specific number you should commit to memory. According to the official Glue documentation, Glue automatically enables grouping once there are more than 50,000 input files. That threshold is exactly the kind of detail that shows up on a multiple-choice question. Is it 10,000, 50,000, 100,000? It's 50,000. Above that, Glue turns grouping on for you, even if you forgot to set it yourself. Last big concept for this episode, and it's a critical one. Imagine your nightly Glue job is reading from an S3 bucket that grows by 5 gigabytes every day. Without some kind of state tracking, every night's run would reprocess all the historical data plus the new stuff. That's wasteful and slow. Glue's answer is job bookmarks. Think of it exactly like a bookmark in a paperback. It sits at the last record you finished, so tomorrow's run only reads the new ones. Here's the official definition from the Glue documentation. Glue tracks data that has already been processed during a previous run of an ETL job by persisting state information from that run. That persisted state information is called a job bookmark. 2 key words there: persisting and state. The bookmark is durable across runs, and it remembers exactly what you've already handled. There are 3 bookmark modes, and the exam tests all 3. Enable is the incremental mode. Glue tracks state and processes only new data on each run. Disable is the default. Bookmarks are off out of the box, so every run reprocesses everything. And pause is the tricky one. Pause lets you process new data within a specific range without advancing the bookmark, which is exactly what you need for backfills or for rerunning a date range without losing your place in the production stream. That last mode is the one most candidates miss on the exam. How does Glue actually decide what's new? It depends on the source. For S3 sources, Glue uses each object's last modified timestamp, and anything modified after the previous bookmark is treated as new. For JDBC sources, like a relational database, Glue uses a bookmark key column, by default the primary key, which must be sequentially increasing so Glue can compare values across runs. And here's the most important rule of all: state advances only when job.commit runs at the very end of your script. Forget that one line and the bookmark never moves, no matter how many times the job succeeds. This is the single most common bookmark bug in production, and it shows up on the exam too. Always confirm that final commit call before you ship a job. Let me say that again because it's the single biggest bookmark gotcha. If you forget to call job.commit at the end of your script, the bookmark never advances. Tomorrow's run will reprocess everything you already handled today, silently, with no warnings, no errors. The job looks like it's working, the data is just being done twice. This exact scenario is a classic exam trap. Here's why bookmarks matter in real numbers. NexaRetail's nightly ETL job used to do a full nightly scan of the entire S3 input, about 30 minutes of compute every single night. The incremental run with bookmark enabled now finishes in around 90 seconds, because Glue only reads the objects modified since the last successful run. Same correctness, 20 times less compute, 20 times less cost. That's the difference between a job you tolerate and a job you forget about. Before we recap, let's collapse the 5 traps that trip up real engineers and real exam questions. Cast in ResolveChoice silently nulls every record it can't convert, an easy way to lose data without noticing. Calling dot to DataFrame on a dynamic frame with unresolved choice types gives you weird struct columns or outright errors. GroupFiles has no effect on Parquet, Orc, or Avro because those columnar formats already handle grouping natively. Deleting a catalog table does not delete a single byte of S3 data. The catalog is metadata only, every single time. And setting up crawl event mode without enabling delete object events means deleted partitions reappear on the next crawl because the crawler never sees the deletion signal. 5 pitfalls, all of them exam relevant, all of them avoidable once you know they exist. Quick recap of the exam critical facts. The catalog is 1 per account per region, Hive-compatible and shared by Athena, EMR, and Redshift Spectrum. Classifiers run custom first in your order, then built-ins in a fixed order, with the highest certainty classifier winning if none hit 1.0, and unknown only when every classifier returns 0. Crawl event mode is S3 events into a standard SQ into the crawler, no FIFO, with a cap of 100,000 messages per run. Dynamic frames have self-describing records and choice types, with 5 ResolveChoice strategies. Cast, make calls, make struct, project, and match catalog. GroupFiles in partition fixes small files for CSV, JSON, XML, and IN, auto-enabled above 50,000 files. And bookmarks come in 3 modes: enable, disable as the default, and pause, with state advancing only when job.commit runs at the end of your script. Lock those 6 down and you're solid on the Glue portion of the exam. Now that you understand the catalog as the central source of truth, The next few episodes are going to plug right into it. Athena will let you run serverless SQL over your catalog tables. EMR will use the catalog as its Hive metastore for Spark and Hadoop workloads. And Redshift Spectrum will bridge your warehouse and your S3 data lake using these same definitions. Everything we just covered is the foundation those episodes will build on. Now let's see how well you absorbed all of this with a quick 5-question quiz. Question 1. A Glue crawler is scanning an S3 prefix that contains JSON files. A custom grok classifier is listed first in the crawler's classifier list, but it returns certainty 0.6 on the data. What schema does the crawler produce? Is it A, the built-in JSON classifier runs after the grok classifier and produces the correct schema? B, the grok classifier wins because it's listed first, regardless of certainty? C, the table is immediately marked unknown because the first classifier didn't hit 1.0? Or D, Glue averages the certainty scores across all classifiers and picks the highest? Take a moment to think about it. The answer is A, custom classifiers run first in your specified order, but they only win if they return certainty equals 1.0. If a custom classifier returns anything less, Glue falls through to the built-in classifiers in their fixed order, and the JSON built-in correctly identifies the data. Question 2. A Glue ETL job reads from an S3 prefix containing 250,000 small JSON files. The job runs for hours with poor throughput. Which single change will most improve performance? Is it A, switch the dynamic frame to a data frame to gain Spark's native optimizations? B, convert all files to Parquet before reading them with the existing job? C, increase the worker type from G.1x to G.4x to give each task more memory? Or D, set the connection option groupFiles equals in partition on the dynamic frame reader? Take a moment to think about it. The answer is D. Spark spawns one task per input file. So 250,000 small files means 250,000 tasks and crushing overhead. Setting groupFiles to in partition combines small files into single in-memory partitions during the read, fixing the small files problem in a single line. Bigger workers don't help. The problem is task count, not per task memory. Question 3. A data engineer enables job bookmarks on a Glue ETL job, but every nightly run still reprocesses the entire S3 dataset. The script reads from a dynamic frame and writes to Parquet. What is the most likely cause? Is it A, the S3 bucket doesn't have versioning enabled, which bookmarks require? B, the script is missing job.commit at the end, so bookmark state never advances? C, bookmarks only work with JDBC sources, not S3? Or D, the job needs to run in crawl event mode to track state? Take a moment to think about it. The answer is B, bookmark state is only persisted when job.commit runs at the end of the script. Without that line, every run starts from scratch, even though bookmarks are enabled. This is the single most common bookmark mistake in practice, and the exam loves to test it. Question 4. A team needs to query data sitting in S3 using SQL, run Spark transformations on a managed Hadoop cluster, and also let their existing Redshift warehouse query the same S3 files, all without redefining schemas in 3 places. What architecture pattern enables this? Is it A, replicate the data into Athena, EMR, and Redshift separately and keep schemas in sync manually? B, use the Glue data catalog as a shared Hive-compatible metastore for Athena, EMR, and Redshift Spectrum? C, store the schemas in DynamoDB and have each service read them at query time? Or D, use Glue ETL jobs to push schema definitions into each service via API calls? Take a moment to think about it. The answer is B, the Glue data catalog is a drop-in replacement for the Apache Hive metastore, which means Athena, EMR, and Redshift Spectrum can all read the same table definitions from it. Define the table once, query from any engine. This shared catalog pattern is the foundation of the AWS data lake architecture. Question 5, last one. A Glue dynamic frame has a column user_id that contains both long values and string values, a choice type. The job must write the data to Parquet with a strict schema where user_id is a long, but the engineer wants to keep records with string values for debugging instead of discarding them. Which ResolveChoice strategy fits best? Is it A, cast to long, force everything to long and accept that string rows become null? B, project to long, keep only the long records and drop the string ones? C, make columns, split into user_id_long and user_id_string columns? Or D, match catalog, force the schema to match an existing catalog table? Take a moment to think about it. The answer is C, make columns, splits the choice column into two separately typed columns, user_id_long and user_id_string. So both variants are preserved and the engineer can still inspect the string records. Cast would silently null them, project would drop them entirely, and match catalog would force a schema rather than expose both types side by side. And that's a wrap on Amazon Web Services Glue Core, Catalog, Crawlers, and ETL. If this helped you out, smash that like button and subscribe for more. See you in the next